So in the last class, we discussed about the 7.9, which is the narrow band pass filter. Now we'll take up the 7.10. Draw the frequency response plot for a wide band reject filter having FH equal to 200 Hz and FL equal to 1 kHz. Label the gain and frequency axis properly. So now it is the frequency response plot which we need to do for the wide band reject filter, not band pass filter. So if you really see in the book, right, in the wide band pass filter, we are given a series combination of the high pass filter and the low pass filter. You can see that there is a series combination of high pass and low pass filter. Because you have the series combination of low and high pass filter, right? Because you have the series combination of low and high pass filter, right? We can, write the expression for the V0 by V in as this. Multiplication of both of them, okay? Multiplication of a low pass filter and multiplication of a high pass filter. So this corresponds to a high pass filter and this corresponds to a low pass filter. So it is just a combination of both of them together, okay? Both of them together, okay? So this is AFT will be equal to, so to say, the gain for both of them together. That's why he is taken it as 4. Now going in the same way, if you just see here, so this is the plot which is done for the band pass filter. Going in the same way, this is the narrow band pass. Then you have the band reject filter. So wide band reject filter, he has just given the design, but he has given the figure. So if you see here, one is a what you call this is a differentiator. Differentiator just means the high pass filter. This is integrator, which is a low pass filter. High pass and low pass are connected in parallel. So you can see that one above the other. Okay, they are connected in parallel. We are giving input here and they are connected in parallel for band reject. For band pass, they are connected in series, high pass and low pass. For band reject, they are connected in parallel and then they are summed, okay, added together. Whenever we say the connected in series, then it will correspond to multiplication. And whenever we say parallel, it just corresponds to addition, okay? So when they are connected in parallel, we are just adding the gain of each of them, right? So therefore, we need to write the addition of them, that is AL, the gain of the low pass filter plus the gain of the high pass filter, or response of the low pass filter plus the response of the high pass filter will give us the total response of the overall band reject filter, right? So we need to do the summation of that, right? There we did multiplication, now we need to do summation. So each you put separately and add them up, that's all. So each one will be the formula for low pass plus the formula for high pass, add them up and that will give you the V0 by V in of both of them, okay? That will correspond to a band reject filter, okay? That will just correspond to a band reject filter. So nothing big about it. You are given the value of FL, FH, and then for FH, it will just correspond to a, so to say, low pass filter. And for FL, it will correspond to a high pass filter. Okay. We have a higher cutoff frequency for a low pass filter and a lower cutoff frequency for a high pass filter. So using this, design the, write the equation for that and write the equation for this, add them up, and then that will correspond to the frequency response in total. That's all. Okay, that's all. Sum them up and write it. Okay. Again, you need to write the same way in which the what you call plotting is to be done. That is same way. Input frequency, gain magnitude. Now this will be sum of both of them together, and this will be the magnitude, which is 20 log of this value together, right? So you write that and then plot this versus this. That means input frequency versus magnitude on a logarithmic plot. On a logarithmic plot. So in 7.1 7.11, it is draw the frequency response plot for 60 Hertz active notch filter, label the gain and frequency response. So once we talk about the active notch filter, it is the band reject narrow filter, narrow band reject filter, okay, narrow band reject filter, and frequency is given here as 60 Hertz. Now we should consider that 60 Hertz as low as well as high. And also, because it is band reject, we should write the gain for low as well as high. So FL equal to FH is equal to FN is what we need to write for the 60 Hertz. And we design a low pass filter. That means write the formula for low pass filter, write the formula for the high pass filter, right? And then add them up. Okay. So if you want me to go back to that, low pass filter and high pass filter response, okay, we can just go back to that and check what it is. So this is used for the high pass filter, AF into F by FL divided by root of 1 plus F by FL whole square. For the low pass filter, you will not have this F by FL, you will have F by FH here. This will not be there, numerator will not be there. In the denominator, it will be F by FH whole square. Okay, that's all. That's the only difference. So this as well as that formula should be added together with same value of FL as well as FH and find the response corresponding to that. So just put here plus AF divided by root of 1 plus F by FH whole square and solve that and get the solution from the same. So we can go for the design of 7.23. Okay, 7.23 is design of low pass filter and it has a cutoff frequency of this. So we have here clearly FH is equal to 1 kilohertz. C we need to choose as 0.01 microfarad. Calculate the value of R, right? So now only change is here 2 kilohertz. So this value will be C. R will become half because it's coming in the denominator. So it might be, it'll just correspond to something like 7.9 kilo ohm. Then that means you can use a 10 kilo ohm pot or potentiometer. Okay. So let us go to the next one. Design a second order low pass filter at a frequency, cutoff frequency of 1.2 kilohertz. Second order. So second order is the next topic. So this is second order low pass filter. So corresponding to this again R2 equal to R3 equal to C2 equal to C3. C2 equal to C3, R2 equal to R3. C2 equal to C3 you can choose again 0.01 microfarad. Find R2 equal to R3 equal to R and that will be the value of the resistance. Now what is it which is given to us? Is a gain given to us? No, it's not given, right? A gain is not given to us. So we can choose whatever gain you feel like, okay? But however, it is only the, FH values we need to find and then might be you can choose you can find the value of RF and R1, right? So if you want a gain of, 2, then might be you can choose properly RF equal to R1. I think for Butterworth, I think it is, 1 point standard value. AF value is 1.586. Okay, AF is equal to 1.586 for Butterworth filter. So 1 plus RF by R1 will be the values to calculate. R1 you take it as say 1 kilo ohms. Then RF will be correspondingly something like 5. 86 kilo ohms. Okay, 5.86 might not be available. Whichever is the nearest available, you can choose, or you can use a 10 kilo ohm part. Sorry, 1 kilo ohm part, and correspondingly, you can try to choose the value of vary the part so that RF is equal to 0.586 kilo ohms. Or you can choose R1 equal to 10 kilo ohms, then RF will be equal to 5.86 kilo ohms, and you can use a 10 kilo ohm part, and that will suffice. So whenever we talk about design, please remember that it is the resistors, the capacitors which we should find. Okay, in the design, we should find the resistors and the capacitors. Okay. Next, we go for 7.25. Design a first ordered high pass filter at a cutoff frequency of 400 hertz and a pass band gain of 1. Whenever we say pass band gain of 1, please remember that it is the voltage follower only. RF is equal to 0 and R is open and RF is short. Okay, so that is voltage follower. Then corresponding to this cutoff frequency of 400 hertz, we need to design a high pass filter. So first ordered Butterworth high pass filter. Formulas are not going to change as far as those things are concerned. So again, AF is equal to 1 plus RF by R1. This is equal to 1. So RF will be equal to 0 and R1 will be equal to infinity. That means R1 is open and RF is short. Okay. So then we need to just find out the value of, you need to write there. Okay. RF equal to 0 and R1 equal to infinity. You can write, or at least you write voltage follower. We'll use voltage follower. Okay. R and C are to be found. Okay. Formula is same. FL is equal to now we are talking about high pass. You write FL is equal to 1 by 2 pi RC. Okay. Choose the value of C and calculate the value of C. So the design is not going to change. The value is not going to change there. It's just the same. Okay. So value of finding that value is just the same. Okay. Here AF is equal to 1. When AF is equal to 2, we had this value of R1 equal to RF equal to 10 kilo. When AF is equal to 1, then R1 will be infinite and RF will be equal to 0. That is, we use a voltage follower. Find the value of R and C corresponding to, whatever we have the corresponding values there, right? So that's what we need to find out. Okay. So then we will go for the next problem. Design a wide band pass. Okay, there 7.26. Design a second order high pass filter at a cutoff frequency of 1 kilohertz. Okay. So as soon as you say second order, then AF is equal to 1.586. AF is equal to 1.586 for the Butterworth. Okay. Second ordered filter, second ordered high pass filter is here. So AF is equal to 1.586, whether it is low or high. This is the standard value, right? Again, now when we talk about second order, then it will be R2 equal to R3 and C2 equal to C3. C2 equal to C3, again you choose the value, whatever you want, 0.01 or 0.0047 as is chosen here, and find the value of R for the value of FL given to us in the problem. For the value of R given to us in the problem, which is 1 kilohertz. Okay, might be in the here it is given for the value here also it is 1 kilohertz, no difference. So there also it is 1 kilohertz. Fine, no problem, whatever. Okay, so please remember that values in the internals might be changed. Fine. Then we will go for the next one, that is 7.27. Design a wide band pass filter with FL equal to 400 hertz, FH is equal to 2 kilohertz, and a pass band gain of 4. Also draw an approximate frequency response plot for the filter. Okay, this is what we have here, wide band. So let us see the wide band filter. Higher order we don't have. Okay, band pass in this wide band filter. Fine. So whenever we talk about the band pass filter. Please remember that these two are in series. Series means gains get multiplied. Gains get multiplied. So the same as this, almost same as this here. Wide band pass gain is 4 and FL, FH are given here. Gain is again 4 here. FL, FH are given as 402 kilohertz. Here it is 201 kilohertz. Only that difference. Okay. Then frequency response plot. Okay. Same process. We need to write R is equal to 1 by 2 pi FLC. A low pass filter was designed, therefore the same values of resistor and capacitors can be used, that is R dash is equal to 15 and C dash is equal to this, right? Then the high pass filter, it can be designed by using FL is equal to 200 hertz here, but there it is, in our problem here it is FH is, FH is, where is FH here? We are talking about this. FH is 2 kilohertz. In this problem, it is given as 1 kilohertz. So accordingly, this value will get changed for the formula, which is, FH is equal to 1 by 2 pi R dash C dash. FH is equal to 1 by 2 pi R dash C dash. Okay. Substitute in that, choose C dash equal to 0.01. Naturally, R dash will become, for 2 kilohertz, it will become half of this, right? Then for the low pass filter, again choose the value of C equal to 0.05 microfarad. We are just renaming them as for high pass, we are low pass, we are writing R dash C dash. For high pass, we are using RC. So name them separately for low pass and high pass. That will solve the problem. Okay. So then find the value of R for that 400 hertz value. Choose C, might be if you want 0.01 or 0.05, whatever you like, right? You can choose and that will finish the design. But however, the value of AF here for the second ordered filter, this is a second ordered filter which is given to us as the what you call a wide band filter. So AF is given as 4. Here also it is, I think, uh, given as 4, right? So you can use the final formula for the response, right? This is the AFT is equal to 4, F by FL divided by all this. This is the response. You can calculate it. You can try to plot using, this table, okay, and do the final solution. Fine. So then we'll go for the next one. Design a narrow band pass filter so that FC is equal to 2 kilohertz, Q equal to 20, AF equal to 10, right? So narrow band pass filter is the next topic here. Okay, this is narrow band pass. Formulas are given, right? Choose C1 equal to C2 equal to C equal to whatever 0.01. R1 you can calculate for the frequency given there, center frequency given there. How much is the center frequency given? Narrow band pass filter 2 kilohertz, right? Q is given, AF is given, all the values are given there, right? We need to just substitute and get the value of R1 and R2 and R3, and then AF is equal to R3 by 2 R1. So you can try to find out the corresponding values. Okay. So again, gain AF, however, must satisfy the condition which is AF by 2 Q square. This need not be, we need not bother about this. We can just choose the value of C and find R1, R2, R3. Okay. Then if you're changing the frequency, then we need to find out this value. However, we are not changing the frequency here. Okay. So in this particular problem, and that will solve the. Then we have 7.29. Design a wide band reject filter using the first order high pass and low pass filter using FL is equal to 2 kilohertz and FH is equal to. So as I said, band reject filter will be series combination, the parallel combination of the low pass and high pass. That means addition of the both their V naught by V ins. Okay, low pass and high pass, and correspondingly we need to design for this. Okay, so that will be here the okay band reject filter. So again, we have to follow the same process, whatever is given in this example 7.9. It is FH equal to 200 hertz, FL is equal to 1 kilohertz, right? But here those values are changed. So it is, so to say, 2 kilohertz and 400 hertz, right? So here it is doubled, right? These two are doubled there, and we need to find the values. That's all. Okay, use the formula and find. Then you have the design a 400 hertz active notch filter, right? So then you go for the next topic, narrow this thing. Fn is equal to 1 by 2 pi rc. Choose the value of c, find the value of r. All throughout, if you see, it is this formula only. Fl, Fh, okay, Fn, whatever, Fc, whatever. You have this formula only. Only in the second ordered case, you'll have two set of resistors, R2 equal to R3 equal to R, and C2 equal to C3 equal to C. That's all. So formulas do not change much. Only the response formula might change. One might be addition, another might be multiplication, depending upon whether it is band reject and or band pass. The value of AF, if it is second ordered, the low pass, then we'll have 1.586 for what you call low pass as well as high pass. AF will be 1.586, but band reject and band pass, you might have different value. Okay, so uh, what do we have? Okay, notch filter is over, right? Then phase shift oscillator. This is not the topic which is for our discussion.